This is on dicarbonyl compounds in synthesis and is found on section 17.7, page 864 of Ogilvy's mechanistic patterns. Here are examples of 3 dicarbonyl compounds: pentane 2,4-dione, acetoacetic ester, and malonic ester. Each of these compounds have acidic hydrogens at the alpha carbon because the alpha carbon is flanked by 2 carbonyl groups. Each of these alpha carbons are easily deprotonated by hydroxide ion or the ethoxide ion. The blue dot represents the alpha carbon that becomes a nucleophilic site. This site is resonance stabilized as shown by these resonance structures. These dicarbonyl compounds are good nucleophiles for alkylation reaction by the SN2 mechanism, so only the least hindered methyl and primary alkyl substrates will react fast. The first step is deprotonation with potassium ethoxide or potassium hydroxide to make a nucleophile that attacks an alkyl substrate in the second reaction. The process of deprotonation and alkylation can be repeated for the second hydrogen on the alpha carbon, so alkylation can be done twice with different alkyl groups. And remember, only the least hindered alkyl group are reactive. The acetoacetic ester synthesis allows an alkyl group to extend its carbon chain by 3 carbons. The synthesis involves alkylation and decarboxylation, involving heat to remove carbon dioxide, and the product is a ketone. Here is the alkylation step. First, it requires deprotonation of the alpha carbon, followed by an alkylation by an SN2 reaction. Here is the decarboxylation, treatment of the ester with a base followed by acid and heat to decarboxylate. More about these base-catalyzed reactions later. The malonic ester synthesis allows the alkyl group to extend its carbon chain by 2 carbons, and the product of the synthesis is a carboxylic acid. The steps are very similar to acetoacetic ester synthesis. Here is the alkylation. It requires a deprotonation of the alpha carbon, followed by alkylation with an SN2 reaction. Here is the decarboxylation step. Treatment of both ends of the ester, followed by heat to decarboxylate, gives the carboxylic acid product. Let's take a look at the base-catalyzed hydrolysis before decarboxylation. Hydrolysis before decarboxylation synthesis. A ketone with hydroxide or ethoxide base will lead to an enolate ion. The reaction is in equilibrium, which favors the ketone reactant. The ester reaction with a base was previously discussed in Chapter 15. This is the base-catalyzed hydrolysis to produce carboxylate anion. In this example, it is a carboxylate dianion that is produced. Treatment of the carboxylate anion or the carboxylate dianion with acid leads to carboxylic acid or the dicarboxylic acid. The next step after base-catalyzed hydrolysis and the production of the carboxylate anion is to acidify the carboxylate anion or the carboxylate dianion to produce the carboxylic acid. This is followed by heat to decarboxylate. Notice in acetoacetic acid synthesis, a ketone is produced that extends the alkyl carbon by 3 carbons. Notice in the malonic ester synthesis, a carboxylic acid is produced that extends the alkyl carbon by 2. This is the mechanism of decarboxylation in acetoacetic ester and malonic ester synthesis. Both mechanisms follow the same electron rearrangement. First, note, to set this molecule for easy to visualize mechanism, twist the bond between the alpha carbon, blue dot, and the carbonyl carbon, red dot, of the carboxylic acid so the carbonyl oxygen is pointing down and away to the right, as shown in this example. The carboxylic acid OH group points up, and the hydrogen of that group is pointing towards the oxygen of the other carbonyl group, the ketone or carboxylic acid. On heating, the electron rearrangement starts with a proton transfer from one oxygen to the other using the carbonyl pi bonding electrons as shown by the first arrow. The second arrow synchronously breaks the hydrogen to oxygen bond to transfer these electrons for a pi carbon to oxygen double bond. The third arrow forms the enol bond, thereby releasing carbon dioxide. Both synthesis results in the formation of an enol, and a transfer of hydrogen from the enol to the alpha carbon gives the corresponding ketone for acetoacetic ester synthesis and the carboxylic acid for the malonic ester synthesis.